Hey folks, welcome to Advent of Code in F Sharp. Day 22 already, which means we are down to the 4 last puzzles. Mixed feelings. It's been a great month. Yesterday we ended up having a bit of a performance issue, like everybody else probably, during the. What was it again? Oh yeah, the Dirac the quantum universe thing. Did not get around to solving part 2 yet. We had a board game night with my family, and that was fun as well. No energy to spend on puzzles anymore. So let's take a look at day 22, shall we? Reactor reboot. Operating at these extreme ocean depths has overloaded the submarine's reactor. It needs to be rebooted. The core is made up of a large 3D grid made up entirely of cubes. One cube per integer 3D coordinate. Yep, sure. Each cube can be either on or off. It's a 3D game of life. Or 3D cellular automata. Yeah, sure. Have we seen it before? Last year, day 17. Let's take a quick look. Was this a fun one? Yeah, that was a fun one. To reboot the reactor, you just need to set all of the cubes to either on or off by following a list of reboot steps. Okay. Each step specifies a cuboid, which is a set of all cubes that have coordinates which fall within ranges for x, y, and z. Okay, so that's just a range for 3 coordinates. Yeah. For example, given these reboot steps. On, off, and these are all ranges, so these are all cuboids. Turns on a 3x3 cuboid consisting of 27 cubes, yeah? Yeah. Wait, so we don't really have rules? Our input is just a sequence of cuboids and whether or not we should turn them on or off? You can turn on a single cube with a really small cuboid, yeah. The initialization procedure only uses cubes that have x, y, and z positions of at least -50 and at most 50. For now, ignore cubes outside this region. Okay, so we have a finite grid or a finite space. We have a larger example. And I mean, for part 1, let's just do the infinite thing. Yeah, let's do the infinite thing because I know what's coming probably for part 2. But let's clip our cuboids. If we do stuff with cuboids, let's not do stuff if we fall outside of the -50-50 ranges. Yeah. So we execute reboot steps afterwards, considering only cubes in the region. Or we can do it for the entire universe, because there's no impact, there's no interaction between cubes. So I think we can just do it and do it in an infinite grid and just check this little cuboid at the end. This sounds like a solvable problem. Let's take the first small example. Where is my code? There we go. I make videos of myself not because I like it, but to do audio checks. To make sure I have not put myself on mute, stuff like that. There we go. Am I live, dear Twitch? Yeah. Okay, cool. So yeah, let's parse this, or let's maybe first take a look at our actual input to make sure there are no gotchas like a couple of days ago with that image enhancement thing. Yeah, we only do -50 to 50. Look at these coordinates. That's a bit out of range. Maybe we should do for part 1, do some filtering, because most of these ranges are ridiculously large. Yeah, I think these might be the only relevant if there's no overlapping. Doesn't look like it. Yeah, we'll figure that out. Let's just grab that for now. Plop it in. Text file somewhere. 420 lines. Would that be 20 lines of easy stuff and 400 hard things? Probably. But anyway. See, this reads, yep. Let's parse. So let's define some types first. I like the idea of explicitly modeling a cuboid. So that's a range for the 3 axes. Is integer going to cut it? Yeah, I think so. So range is just a tuple of integers. Cuboid is 3 ranges, one for every axis. We have x, y, and z. What else do we need? Maybe a full instruction. Is a command and one of those cuboids. Should we call it cuboid or range? Let's call it cuboid. What is a command? That's just a bit or a boolean, sorry. On or off. What else do we need? We need a universe or grid. We need a 3D coordinate. Let's stay in the integer world for coordinates. Yeah, why not? And a grid is just, let's do the infinite thing from the get-go. Mapping coordinates to commands. Command sounds bad because we use it both as an actual command and a state. This is the command part. We turn something on or off, but we also have the state. We can use the same thing for both, right? It's not that big of a deal. Yeah, so let's interpret this as both the command and state. Yeah, let's parse into these types. Let's send these to the REPL so REPL knows about these types. Let's start playing. So, parse instruction, what would that look like? Parse on space, that's a good start. Let's do that outside of the function definition first so we can play around with it. Let's grab one of the instructions. That'll work a bit better. That's not what I wanted to do. This is better. So we have an instruction. If we split it on space, we get what we want, yes. So that's 2 things. The cuboid text and where is this bracket? There we go. That's the command we need to parse and the cuboid we need to parse. Yep. So our command is let's write a parser for that. Just use the function pattern match syntax here. On gives us on, and off gives us off. That should work, or at least for the cases. Where is it not finding command text? Oh yeah. Yeah, we can parse ons. We'll probably be able to parse off, so that's the command part. Now the cuboid part. Split on. Let's split on comma. Let's dive a bit deeper. We can just ignore the x, y, and z equals because the positions align with the coordinates and there's no shenanigans going on. Let's do a quick check. A shenanigans check it's always XYZ. Of course, it's always XYZ. That would be that would be quite the instinct. Okay, so let's do some more on this. So let's get rid of the things before equals, or we can just do skip to, sure. What is that? 0, 1, 2? Is this what we need? Yeah. Okay, and then let's split that into the two numbers. So that's split on a string with two dots. No? At least if I balance my parentheses. That's 3 times 10, 12. That's not correct, right? Oh yeah, it is. Never mind. So now we have our numbers as... We have our numbers as strings. Now we need our numbers as integers. That's probably one way to do it. Yes, so let's just do a big destructure here. So we have x min, x max, and the same for y and z. And a separator should be a semicolon, not a comma. Is this parsing into what we think is parsing into? Quick sanity check. 10, 12, 12, 12, 12. It's a bad example. Let's do 1, 2, 3, 4, 5, and 6, 6, 6. 6. One more to keep it happy. Yeah, looks correct. Cool. And let's parse or put everything in a cuboid now. So cuboid was something with an x, which is a range. Ranges were tuples, so that's just x min, x max, and the same for y and z. Y. It's only 2 occurrences, so let's just do it the low-tech way. There we go. So we have a parse command. This is a parse ranges. Yep, I think this is a nice parse. So this needs to go inside our parse. This can go to the examples. And everything here can shift, so that's part of the function. It's not happy? Why is it not happy? Let's see this in action again, now that we put it in a function. 1, 2, 3, 4, 5, 6, 6, 6. We return the cuboid, but we should also return the command. What was our type again? Instruction. There we go. So this parses something into a string into an instruction. Let's make it very explicit. What is this problem still? This example not a list. Oh no, it's an array. Cool. Cool. We have parsing. Let me put it in a test real quick. Equals what? Let's just run it and verify it by hand, and then just copy paste it into our expected output. That's not really calling the shots, but I can still make sense of an example this small. I won't be biased at all. Oh, come on. Okay, now you can format if you want to. There we go. Still works. Cool. We can parse. That's part 1 of today. What's next? Do we have an initial state actually? They're all off. Okay, that's easy. Should we do the same thing as we were doing with the... Sorry. We were doing something with a cellular automata not that long ago, and we had a map for the infinite thing, and we kept the map super small by only tracking the Alm coordinates. So now that I hear myself say this, it's not really a map then, but it's just a set of all the coordinates that have an Alm state. Should we do it like that here? We could. We could actually. Nah. Performance-wise, it won't matter that much. So everything is off from the beginning. Cool. Now we just need to run our instructions in sequence, yeah, on an empty grid, or a grid where everything is turned off. Yep, I'm just thinking about the minus 50 plus 50 thing. Ignore cubes outside of this region. How will we do that? By just making the cuboids we get as input smaller? Or by filtering out the cuboids that have problems? Nah, yeah, performance-wise that would be the smart thing to do, but part 1 will not have a performance thing. I just made an assumption. I should make that explicit somewhere. Or I can go for a bug hunt for hours, like with the image enhancement algorithm. So we can just do everything and select the 50-50-50 cuboid. In the end, no performance hit. Yay. So that's my assumption. That's how I'm gonna tackle it. Even part 1. I think I'm making my life harder, but I don't mind. I have time and I'm feeling fresh today. Anyway, we have instructions. Let's build an empty grid. Yeah, let's build an empty grid. And now, what do we need to do? We need to run all the instructions on a grid. So it's we can use a fold, So we can fold over the instructions. Yes. Using a function apply instruction, and the initial state is our empty grid. And apply instruction should be a function that takes grid and instruction. Cool. It is a function that takes the grid and an instruction and returns an updated grid. Yeah, I think it's still correct. What do we need to know? Instead of doing a neighbor search like we usually do in these Conway-like things, we have the cuboid which we want to do something on. So that makes our life a bit easier actually. Do we need to grab anything out of the map? No, not even. We need to generate all the locations in the cuboid. Track the state. Yeah, this is going to be a performance problem. I can already, like, my spider sense is tingling. But for part 1, let's brute force it. So instruction is an on or off thing. Instruction has a cuboid. And we can just, for a naive first pass at the algorithm, we can just generate all coordinates in that cuboid. We can do some optimizations here. If we know we're going to turn stuff off, that means just removing everything in the map that is on and stuff like that, but not for now. So we get a cuboid. Let's first write an all coordinates in a cuboid function. So that's just a flat list. Let's write a comprehension iterating over the 3 axes. So this is an x. So for x in yeah, and it's x dot first. Yeah, I'm gonna not rapid type around that. Let's just do it like this. So that's looping over the x's, and the y's and the z's are just the same. And we just return xyz. Let's update everything. This is always dangerous. Just copy pasting, but I think we can manage. This returns a list of coordinates, yeah. Yeah, that still aligns with the types you expect. Let's try that. So we had a cuboid. Yeah, it's a small cuboid, so let's play around with that one. So that's a parsed instruction. If we grab the cuboid from that instruction and pipe that to all coordinates and make it a little bit smaller. So we go from 1 to 2 to 3 to 4 to 5 to 6. Okay, so 1, 3, 5, 1, 3, 6, 1, 4, 5, 1, 4. I think that might be correct. So these are all the coordinates, and we need to just update the state to whatever is in the instruction. That is easy. So we have the cuboid. We grab all the coordinates. We build a tuple with that coordinate and the new state, which is called command, but that's okay. So these are all the tuples, and we need to update the grid. So let's do that in a 2-step process. This is the updates we need to do, and now for every update, apply this to the grid without any optimizations first. That'll work, or that will be correct. I don't know if it'll be fast enough, but we'll see. What does a map fold? Oh no, we don't need to fold over a map. We need to fold over a sequence. We can update the grid, and our initial grid is grid. As you can see, I'm a fan of folding. So let's write an update grid function that takes, what was it again? The grid and an update. An update is a location and a state. And it's just a map.add at location this state. What is it not liking? Coordinate list tuple. Whoa, what is that supposed to be? Oh, we need to map, of course. We need to map over every individual coordinate. Yeah, that looks better. So what does our apply instruction look like now? We grab every coordinate in the cuboid. Yes, then we say the new state for that coordinate is whatever we get in the command. Yes, and we say update our grid. I think that might be correct. There's a lot of offs in there. Is that something we expect? The small example, what are we actually doing there? One thing I want to see. No. So blah, 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 blah. After the last step, 39 cubes are on. What is actually the thing we are looking for? How many cubes are on? So let's count the on cubes. This should give us what? This should give us grid. So this is the grid in the end with a lot of offs. And if we say grid, number of bindings, no. Filter, that's something we might want to do in the real code as well. What does filter take? 2 arguments. 2 arguments, okay. So that's a location and a state should be on. These are all the on things, and if we count the length of that vector, we should get 39. 39, that looks correct. The on count, not on send, on count, 39, cool. Oh yeah, this is also a biggie. Let's do the minus 50 plus 50 thing somewhere. Let's do it down here. So another filter. We don't need lock on this filter. We do need lock on this filter. Lock is an XYZ coordinate, right? Is that correct? Yeah. That should fall within the 50 range, right? So X, Y, and Z all should be in the 50 range. Did we have a range thing? We have a range thing. So let's use that. Minus 50, 50. Is it inclusive or exclusive? Let's verify that real quick. What is it not liking here? Again, parentheses, again, parentheses. Oh yeah, and this needs a range and a location. That's why my compiler is not very happy. Cool. Initialization procedure only uses cubes that have X, Y, and Z positions of at least minus 50 and at most 50. That sounds like they are inclusive. That's not how our range works. Yes, that is how our range works. If they are the same for every dimension. I was expecting like 6 coordinates or 6 points. No. It's always minus 50, 50. So X should fall between, Y should fall between, and Z should fall between. And these are not vectors, these are points actually, right? Why did this compile? Why is this compiling? Oh, because my list is a single element list. That's not what I was planning actually. Yeah, there we go. So point should just be at least minimum and at most. Where's my and? I don't write ands that often. Okay. So point should be at most max. Cool. Still 39, still 39. Let's grab a larger example. and see if that works. Do we know something about this example? Yes, we know the number of on cubes. Uh-oh. I smell a performance problem here. We are naive in two areas. One is we keep a lot of unnecessary state. That's a small fix. We can just get rid of that unnecessary state with a filter like this every time we update. Or even, no, we can even do better. Here where we update our grid, we can only take a look at, we can like have two different kinds of logic. If we are going to turn things off, we can optimize that differently than turning things on. On, we just have to do. We have to remember for every coordinate that is on. But for off, we don't have to like take a look at every coordinate per se. We can just loop over all the on coordinates we have and just verify whether or not we should turn that single coordinate off. And it looks like we are going to need to do something because this is eating up CPU pretty badly. And the second optimization, so this is an optimization on the data structure we use. The second one is for part 1, we can ignore most of the instructions, if not 400 of the 420, I think. So for this example, I think if I look at cursory read of the instructions, these are relevant. And these like all fall outside of the range and don't even touch the range, right? Yeah, I think so. So is this the same with our input? Should we risk it? Yeah. We are going to need to write the optimization for part 2 probably. You know what? I'm going to like pretend these two last lines don't exist. And let's run it again. How big is our space then? 100 by 100 by 100? That should be doable, right? Let's just rerun everything. No, that still looks bad. That still looks pretty bad. How can this be so bad? It's like 10,000 points max for every instruction, right? Yeah. How can this be so bad? Okay, anyway, stop. Revert. Let's get those big boys in there again. Okay. Let's start optimizing. We have the small example working. I'm going to encode that fact by writing a solve function here. And this is everything we need to do. And let's return the on count. Let's use whatever we get as input as the actual thing we parse. There we go. So this is our solver, or naive solver at least. And if we solve the small example, that should work, and we should like to keep it that way. 39, I guess. Why? Oh, I need to remember how to write tests. I'm sorry. There we go. Yeah, so unit means everything is green. Let's verify that to be sure. Yeah, so example works. Let's check in our code. Naive solution. Needs some performance tweaking. A couple of things I can think of we already discussed. I'm gonna do the the easiest things first. So every step in the instruction where we do stuff here, we apply a single instruction to the grid. And then we update our grid. Let's, after we do that, say, and we only keep the things that are on in our grid. So it's a set of all locations actually, but we use a map because I don't know, I like maps probably. I think this might already be much better. Let's see how far we get with this. Yeah. So our tests still work. That's a small comfort. Let's try to solve the larger example now. Let's put in some kind of feedback so we know what's happening. So solve, that's this thing, fold. Let's print something inside apply instruction. Okay, let's print out the instruction. That's good enough, just so we can see what's happening. Okay, it is working, but it is very slow, which is a bit surprising. Those are not very... Oh, you know what? We could do like an even bigger optimization, but it's going to take maths. Instead of having a map of coordinates be our data structure, we can have a map of cuboids. But that would mean we have to invent or rediscover cuboid mathematics. What happens if you have like overlapping cuboids? There's like a... Oh no, that actually will be pretty tricky to do. Subtraction of two cuboids is not really a cuboid. That's like 1, 2, 3, 4 different cuboids. Or 3? 3 cuboids. We could split a single cuboid into 3 or like 4, where one of the 4 is a nibble of another cuboid. If you do like something like subtraction, addition, same thing. I think if you add 2 cuboids that have an overlap, that results in one cuboid staying the same and the other one becoming like 3 smaller cuboids, everything that's not part of the first cuboid. I think that might actually work. It sounds like something fun to do, but it sounds like we will not be finished in 5 minutes if we go that route. Oh, actually we were done. How many instructions is this? 1, 2, 3, 4, 5. These are actually 20 instructions. I think we have something that is performant enough maybe to solve part 1. So before I start thinking too much about the problem, let's get rid of everything that I think or hope is irrelevant. And let's solve our input. Where do I solve stuff? Here we go. So let's run everything, load everything in the REPL again. And let's see how far we get. I have not verified whether those 400 last instructions all like are easy to, or if it's possible to skip them for part 1. I'm going to assume we can. So once we see these, we might be done. But yeah, cuboid maths, that sounds like something fun. Let's start drawing it out while we wait for my super fast algorithm to complete. Okay, 25% of the way there. I was thinking we could maybe even do something smarter and just not have a map, just do cuboid maths all the way. We have like an empty cuboid to start with, and then whenever we see on, we do some kind of addition. And then we have a set of cuboids. Oh yeah, that's actually the same thing as our grid. Never mind. It'd be the same. Let's first do this in 2D with our 2D cuboids, then I don't think it's called a cuboid, but whatever. So if you have two non-overlapping cuboids, yeah, I'm gonna do cuboids. So these are two cubes. If they don't overlap, you just have a set of two. Interesting stuff happens when you have overlap. If you have overlap, what can you have? Cases. You can totally consume another cuboid. Yeah, there can be one can be bigger, and then the small one. Let's first do the on case. So what happens if you add stuff? If it subsumes another cuboid, it just stays the same. The biggest cuboid remains, smallest cuboid is forgotten. Cool. What else can we see? Overlaps. If you have like a small cube overlapping, then I think one cuboid can stay, and the other one splits into 3 remaining cuboids. Also in 3D, I think. Yeah, I think. So our mission, should we choose to accept it, is to keep state or a data structure that maintains cuboids, but only on cuboids. So we have a set of cuboids, and every coordinate in those cuboids represents all the possible on states. And then we just invent cuboid magic or cuboid maths. Can we find cuboid addition? Yeah, it's actually a thing, adding and removing cubes. So I think that is literally what I'm trying to reverse engineer here. Oh, come on, give me cuboid addition. Give me algebra for cuboids. Oh, we have an answer. Cool. Let's see whether or not the assumption holds. The assumption holds. Cool. That is part 1. Let's reverse back into the bigger data set, which will need some tweaks. But I'm first going to commit part 1. So we did a bit of a cheat by doing some... It's not a cheat, but we did some intelligent problem solving. Let's call it that. So 22 part 1 done. But now we need to do even more intelligent problem solving. We need to figure out how to make this performant. Probably. Let's take a look. Part 2. Now that the initialization procedure is complete, you can reboot the reactor. Everything starts off again. Now we need to run all the things, not just the mini dataset that was already causing performance problems. So now, yeah, search space becomes significantly larger. We need to become smarter, or our algorithm needs to become smarter. And we are back into number crunching territory. Okay, we have like a big problem to solve, a really big problem to solve, and we have a small thing we can verify, and that's if we select the 50 by 50 by 50, no, the 100 by 100 by 100 initial grid, but while running these huge things, we should still have some cubes we can verify. So this was a predictable part 2. And I think the cuboid mathematics thing sounds really fun and potentially one of the only ways to make this problem tractable. But that would mean studying. This looks like a really interesting movie, but I'm not gonna watch too much YouTube on stream. Do we have articles? You know what? I'm just gonna put that on somewhere offsite while I think about the problem. Or no, actually, it looks pretty harmless. Let's get it up on screen. It's only a minute long. Yeah, this is exactly what we're trying to do. Oh yeah, you don't only have three parts. Cuboid math is significantly more advanced than I thought. I don't know if I want to go that route then. How many cuboids does this transform into? It's like 1, 2, 3, 4, 5 resulting cuboids. Is there a general way of doing this? And this is surface area. We don't need surface area. We need the actual cuboid algebra. I want to work in the cuboid world. Joining two square cubes into a cuboid. That is something close to what we want. Determining whether two cuboids intersect. That will be a basic dimension comparison. Is this really how you do it? In my head, it was way, way, way easier. Separating axis theorem. We don't need a separating axis plane. No, 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 no. That's overkill. What are we trying to solve here? We get a list of instructions. So those are cuboids. And they are positive or negative. And we have a bag of cuboids, which is empty at the start. If we get on commands like this, if the bag is empty, we just add the cuboid. But if there is already a cuboid in there, that's when things get interesting. So if we get two ons, two cuboid on cuboids, what happens? Then we go back to the drawing board, I guess. Yeah. And then all kinds of fun thing happen. Yeah, there's one case I have not thought about. What if you have like a cuboid here and it's not overlapping on the corners, but it's like digging into like that YouTube video showed us? What happens then? What's the resulting cuboid set? We're still in the everything is a non case. That makes things a bit easier, or we can ease into the problem. How would we slice this problem? We can always do something like this. Slice the bigger cubit into, take its head off, and then we have this small cuboid, sorry. And then we have like 1, 2, and one before, 3, and one after behind is 4. So that results in 1, 2, 3, 4, 5, 6 cuboids. That's a lot. That's harder than I was anticipating. That's what I mean. And if one operation already can split our search space into 6, 400 operations can also be quite catastrophic, right? Do we need to merge cuboids back again? No, I don't think that makes much sense. What's the trick here? What's the trick? Is cuboid worth investigating? Sometimes the date title contains a hint, but it's not. It's no hint today. I kind of liked the cuboid mathematics idea, but in practice, No, I'm not well versed enough in cuboid mathematics, sorry, to actually start tackling this without reading up. Are there naive optimizations we can do, which we were thinking about first? Because the cuboid thing is a whole other level. Just enumerating all the coordinates is actually the pain point already, right? If we try to enumerate all coordinates, that's what is eating our performance and keeping it in a data structure as well. But if that is the case, then we have no other option than to do something smarter. Shoot. Four hundred cuboids. Can we do? We can do something else. We know, or the problem today is easy in the sense that the rules don't look at neighbors and stuff like that. So say we take this list of say we take this list of cuboids and just keep it like a list of cuboids in order, and then we just go the other way around. We take a look at every coordinate we are interested in, which is a large data set, yes. It's at least this. Oh no, that's actually a really large data set. I was thinking of doing it the other way around. We have our list of commands, and let's treat those as cuboids, and then generate like an interesting set of data points we can investigate, but it's a pretty big set. It's like this and then some. And then just go through our instructions, and the first or the last instruction that is relevant. So if it meets the if it's in range, if the point is over consumed by this cuboid, we know its state has to be off. And if this cuboid does not match the point, we can take a look at the one preceding that, and if that matches, that's the last state. This actually sounds like not that bad of an idea. Let's see whether or not we can enumerate all points. That will already be a good sanity check to see if this non-cuboid mathematics approach works. So outline of the algorithm, list of all cuboids, of all instructions. We already have that. Then 2, generate all points. And this is the thing we're not sure about, or I'm not sure about, if this is like even tractable to enumerate all points. And then 3, go through the list. So is point an element of an instruction, or all instructions in our cuboid list, or our instruction list, sorry. And if you do that in reverse order, that should work. So let's verify this thing. Can we enumerate all points? I hope so, because I really don't want to figure out how to add and subtract cuboids. Yeah, let's do this for the actual input. Let's parse our input. We don't have a parse, really? We have a parse instruction. Okay. Let's parse instructions, and let's see how big this state space actually is. Let's figure out minimum x, maximum x, and y and z. There has to be a shorter way to do this, but I don't know about it, so it's x dot what is in here. Cuboid dot x dot first. So these are all the x minuses. And the minimum of those minimal cuboid dimensions, that should be what is not happening here. It's an array. Cool. You know what? I've had it with these array and list mix-ups. Yeah, we're just doing some exploratory stuff here. So this is X. Let's do YZ. It can be dirty because it's gone in 2 seconds. Minimum Y looks like this. Minimum Z looks like this. This actually looks correct, right? Yeah, I think so. Those cannot... Actually, it's a search space of what? 100, 200,000 in every dimension? 200,000 in every dimension. That's 5 zeros times 3 is 15 zeros. That's a lot. Let's try to enumerate them anyway. This will still burn our CPU. I've got a hunch. I don't know why I'm preferring sequence over lists here, because I want to dedupe. That doesn't matter. We have to generate them all. Yeah, we have to generate them all. Although, let's see whether or not this terminates. Does it make sense to actually go over all points, or to actually go over all points that ever, or that at least once, are part of the on instructions? That's maybe an optimization we can do already, right? So instead of grabbing instructions, let's grab all the on instructions. So these are on instructions, and those are the only ones that can ever reach an on state. We might get somewhere close without doing cuboid mathematics, I guess. So is this search space smaller? Not at all. Nice try, nice try. No, this goes off. This goes off on a wild performance generating goose chase. That's a shame. You know what? I'm going to print out something here to see how bad it is. So if x modulo 100 equals 0, then print out something. I just want to see how bad it is. I hate it when you're halfway part of a puzzle and you run out of coffee. I should pour larger pots of coffee in the morning. Oh. Is it normal I'm not seeing any printouts? was expecting to see something. Let's try that again. Okay, this is actually doing something, yeah. It's just really, really, really slow. But if it's really, really, really slow, then this is not actually the way to do it. What is this state space again? How many? How large are we talking here? Is this something worth waiting on? No. Let's quickly do some math here. Max x minus minus x and yz. What are we talking? So our small example, which burned our CPU, was 100 by 100 by 100. This is 200,000 in all three axes or in all three directions. 200,000. Yeah, that's 15 zeros for the full state space. That's a lot of zeros. That's what. I can't even put a number on it. Shoot. Okay. It's starting to feel like we have to dive into cuboid maths. If we have 15 zeros and this printout happens at 2 zeros and we don't see a single dot in my output, that means something. That means we'll be here for a long time. I kind of liked my way of thinking though about reverse going through the list, but no, that's not feasible at all. I think I tried every alternative to cuboid algebra, so probably it's time to do cuboid algebra, which I guess is really the best idea. Every time you do something, the worst that can happen is that every cuboid we already know about splits into something like 5 different cuboids. If you do that, that can actually also become pretty huge, right? If the rules are like shitty and they cut every other cuboid into 4 or 5 other cuboids, that's also exponential growth. But at least we are talking cuboids, so we are grouping as much as we can instead of individual coordinates. Yeah. Sounds like a tall order, honestly. Yes, it really sounds like a tall order for my tired, old, not yet fully awake brain. This requires some extra thinking on my part. I'm going to do that in my sofa with some pen and paper, I guess. So as soon as I crack this cuboid thing, I'll get back to you. But until then, I hope you have fun solving today, day 22 of the Advent of Code. I'm curious, are you gravitating toward cuboid algebra? Did you find another way to do it? Maybe not let me know today, because I don't like spoilers, but let me know tomorrow how you solved it. Cool. Thanks for watching, and I'll see you later today, hopefully, if I find a solution for part 2 of Reactor Reboot. Bye-bye.